Hello, everyone. Thank you for joining me in person or online today. In this talk, I'll be presenting a very novel seismic approach that can be applied to monitor a various of subsurface processes related to groundwater, geothermal, CO2 sequestration, and so on. So this method is called passive seismic interferometry. With today's talk, I will be focusing on hydrological processes, but we're also mentioning the potential for this approach to be used for other monitoring applications. Before going on, I'll just want to thank my advisors, PhD and postdoc advisors from MIT and Stanford, as well as my collaborators who made important contributions to the work I'm gonna mention today. So now the top panel is the precipitation in California from 2003 to 2023. And the lower panel is the percent area in California in severe drought developed by US Drought Monitor. So now the shaded area shows the drought period for which you could see California experienced a very strong climate volatility over the past decades, shifting between prolonged extreme drought periods interrupted by very brief, intense storms. So these storms are often driven by atmospheric rivers. So some of you know that I did my PhD on the East Coast at MIT in seismology, and this is January 2022, that's when I first moved to California to do a postdoc, and I was exposed more to the fascinating world of water. So at that time, California was still in a severe drought, and everyone was talking about mega drought. It has actually been demonstrated to be the driest period in northwestern US in 1,200 years. But just 1 year later, at the beginning of 2023, the California was hit by a series of wild storms due to 18 atmospheric rivers. So all of a sudden, everyone was talking about mega flood. So I got very impressed how exciting it is to be a hydrologist. So I looked at it more. Something that caught my interest were all these striking comparisons at that time. So you could see before the drought, the surface reservoirs were at record low. But right after the big storms, the surface reservoirs got refilled super quickly. So at that time, there were all these sentiments on social media about California drought being a hoax or some type of propaganda, because it could be just refilled with one epic year of storms. Is that correct? So I am a geoscientist. We study things happening underground all the time, right? We know this is just surface reservoirs. So what about groundwater? Why do we care about groundwater? Well, as a matter of fact, actually, California's freshwater, 40 to 60% of it comes from groundwater. Also, during hot, dry times, the surface water just evaporates so quickly, and surface water is typically strongly affected by climate extremes. Compared to surface water, groundwater is a more resilient source of water during droughts. Also, if we think about surface water as engineered storage capacity, then the vast space underground would be the natural underutilized subsurface space for water storage. However, the spatial temporal variations of underground aquifer systems is still poorly characterized and understood because it's typically very difficult to measure what's happening underground. So this is the drought map of California in 2021, summer of 2021. But I am a seismologist by training, right? So when I first think about California, actually the first thing came to my mind is never drought or flood. It's typically earthquake, right? So we know there are all those big and small faults in California and with numerous numbers of earthquakes. And for a place like this, there must have been or will be tremendous seismic stations. So these seismic stations were initially designed to study earthquakes and tectonics, but if we could use them to study groundwater, that's gonna be buy one, get one free, right? So in this talk, I'll show you how we can use seismic stations to study groundwater and to what level we could do it and what new insights we could bring with this seismic analysis. Here is a very brief outline. So the first part of my presentation is an introduction to aquifer monitoring. The second part is about this technique we use, the space-time seismic interferometry. In the third part, I'll go into details about several case studies on groundwater in Los Angeles to see what new insights we could bring. And the last part will be some perspectives and ongoing work. So upfront is an introduction to the current status and challenges of aquifer monitoring. So here is a vertical slice just to look at the typical structures of shallow sediments. So this is a vertical slice from the surface to maybe here less than 10 meters. But this type of structures can sometimes extend to hundreds of meters. It shows the tree is not to scale. It shows nicely the layer structures of shallow sediments, right? So we have this type of layers mainly made of clays with very fine courses and with very fine grains. And we also have this type of layers made of sand and gravels with coarser grains. And we know the groundwater is mostly held in the porous space among these coarse grains. So this type of layer are called aquifers. And in comparison, the clay layers typically bear very little. So for a given location, how do we know how much water is stored in these underground systems? So the most traditional approach is to drill a well and measure the hydraulic head, or sometimes groundwater table. So this type of approach is considered to be the ground truth because it's a very direct in situ measurement. However, we know that the hydraulic head measurements is a point scale measurement, right? You measure exactly where you drill. You don't know what's between two wells or what's shallower or deeper. But in practice, it's typically pretty expensive to build monitoring wells. Say in California, to build a monitoring well at about 100-meter depth is $200K, right? Say in California or in Los Angeles, where I study, the aquifers can extend to 700 meters. So the price increases exponentially with depth. So in practice, the spatial sampling is still too sparse to capture the heterogeneity of underground structures. And also we know there are always the privacy issues, and sometimes if you gather data from local growers or landowners, the data could be contradictory to each other. That's always the problem with groundwater well data. In recent years, GPS and INSAR, those type of geodetic measurements, has helped groundwater monitoring significantly. So one famous example is shown on the right side. That's the photo taken in San Joaquin Valley in California, where the groundwater depletion has been very bad due to heavy irrigation demand. So shown on this photo, the signs on the pole indicates the altitude of the land surface in different years. So the land surface was run here in 1925, sent to here in 1955, and to here in 1977. So this photo indicates about 9 meter subsidence within half a century, which is very impressive if we think about it. The basic idea for this type of very drastic subsidence, or sometimes it could be uplift, is that the shallow sediments or aquifer media is acting as a sponge sink in water like this. So by measuring at the surface how much this sponge dilated or squeezed, we could infer the changes in pore pressure and thus the changes in groundwater volume. So as I said, this approach has really helped significantly because of the high temporal resolution of GPS and the high spatial resolution of INSAR. Still, the challenge is that this type of geodetic measurements is a vertically integrated measurement, right? It's only one measurement at the surface. We don't have, say, depth resolution with it. And also, at the end of the day, what people are most interested in is the changes in groundwater storage or volume. However, in realistic, it's still challenging to translate the surface deformation measurements into the groundwater volume measurements. There are also other types of approaches, based on satellite, airborne, or ground-based approaches. For example, the GRACE satellite, the satellite calorimetry, helped a lot to understand global or continental scale variations in groundwater. And sometimes we do this, this was one field trip during my PhD, we do this applied geophysics to find the water table. However, for applied geophysics, typically, the cost is very expensive. Also, these measurements are generally suffering from the low, say, limited vertical resolution. So because I'm a seismologist, so I'm gonna propose a seismic measurement to study groundwater. Specifically, the quantitative measure is called delta V over V. Sorry, feel free to interrupt me at any time. Do you have a question? No, oh, sorry. But just feel free to interrupt me so I could clarify things. So the quantitative measure is called delta V over V. So V means seismic velocity, or just the propagation speed of seismic waves. So we know seismic velocity is dependent on the rock's stress state, right? So when there's more water, higher pore pressure, the seismic waves propagate slower, vice versa. So we could use that to indicate the stress state of the rocks or the pore pressure. The entire delta V over V is the relative change in V. So delta means with respect to velocity at a reference time and location. The idea for us is try to measure the spatial temporal changes in delta V over V and use that to track the spatial temporal changes in groundwater volume. Just to give you a very brief overview, our idea. So typically the observed delta V over V, as shown in the blue line here, is proportional to the hydraulic head as shown in the yellow line here. But we will go into more details about this. So that brings me to the second part about the methodology. How do we measure the spatial temporal changes in seismic velocity? So first, about the time dimension, how to measure delta V over V continuously in time. So the first step is the ambient seismic noise interferometry. The basic idea is that our ground surface is vibrating all the time, everywhere as I speak. It's just most of the time, these vibrations are too weak that we human beings don't really notice, but they are being recorded continuously by seismometers, as shown here. If we directly look at the continuous records of seismometer, they appear very random and somewhat noisy. So these vibrations were considered noise by traditional seismologists. However, in recent years, seismologists have shown that by calculating wave interference of the noise records at two receivers, we can actually retrieve something useful. This is called Green's functions, similar to what we get with real earthquakes. So we call it virtual earthquakes. With that, we can now just deploy the seismometers where we're interested and get the signals by doing the wave interference. So this technique has been one of the most significant changes or advance in seismology in 20th century, because it means that we seismologists no longer rely on earthquake signals or active source experiment, which could be expensive and destructive. Now we just use seismometers, deploy them, and we get all the signals we want. So these ambient vibrations, they are typically generated by, say, ocean waves, winds, or human activities. So those are, omnipresent in space and existing all the time. So this can be a very cost-effective, non-destructive approach. So with this idea, if I try to do the wave interference calculation every day between two receivers, I could extract the Green's functions for each day consecutively. And with that, the second step is called coda wave interferometry. Coda are these later levels on Green's functions. Those are due to waves that have been scattered multiple times underground due to small heterogeneities, and then they arrive on the surface. So coda waves, because they have, traveled a long way in the subsurface, so they sample the medium redundantly. So the most important, advantage of coda wave is that it's very sensitive to small changes in the subsurface. So by calculating these time shifts between the coda waveforms, we will be able to retrieve the delta V over V we are interested. And with coda waves, we do have very high sensitivity to 0.01% order of magnitude velocity changes in the subsurface. I want to emphasize this a little bit because yesterday Andre was just talking to me saying there are people claiming that ambient noise seismic interferometry cannot be used for, say, CCS type of application. So ambient noise interferometry is a very big bucket, right? There are a lot of techniques under it. Typically, when people refer to ambient noise interferometry, they mean mostly the surface with ambient noise surface wave tomography. So those type of approach were first applied in 2003, 2004. With that, typically people are looking at velocity changes on the order of several percent or even 10%. But with the newly developed coda wave interferometry, we're really looking at very, very tiny changes, 0.01% of velocity changes related to, say, environmental processes or very subtle processes in the subsurface. And also benefiting from very recent theoretical development, we're also able to measure the spatial distribution of these small velocity changes. That is the second dimension, how to image delta V over V in space. Okay, so this advance is enabled by this advancement in descriptions of coda waves sensitivity kernels, the so-called sensitivity kernels, which basically describe where the coda waves has been traveling underground. So, for example, shows here, it shows in this bubble, the coda waves travel more, so they are more sensitive to. At later arrival times, the coda waves are sensitive to a bigger area. And with this type of theoretical descriptions, we can relate so this K is the sensitivity kernel. With that, we can relate the delta V over V we are interested in with delta T, that the time shift we can directly measure from our Green's functions. So the format of this equation may seem familiar to you because it is the same for basically all geophysical problems. It means that we can then try to solve an inverse problem where the design matrix consists of all the sensitivity kernels. The D vector consists of all the time shifts we can directly measure. And then the model parameters are the delta V over V at different locations we are interested. So as a very, say, pilot application, here I just use the classic Tarantola recipe to do the to solve the inverse problem. So you can imagine if I try to do this type of imaging on consecutive days, I could get the delta V over V images on each day, which basically give me a spatial temporal type of measurement of delta V over V. Now I want to show you a brief idea of what I mean by spatial temporal variations. So the top panel is a time series of delta V over V measured at this red circle. And now I'll play a small movie to show you the delta V over V time changes at every location in this map. And you will see bluish color corresponding to more groundwater and reddish color corresponding to less groundwater. So the details in this movie will be explained later in my talk. Just here, you can see a general change from bluish color. See here, it's pretty bluish across the study area. And gradually, it transitioned into more reddish. So you could see around 2016, it was pretty reddish, meaning pretty dry across the entire Los Angeles. I also just want to compare this seismic approach with GPS and INSAR regarding the time resolution. So we know GPS is very good at its high temporal resolution, and INSAR excels at its high spatial resolution. Then our space-time delta V over V falls around here. Of course, this resolution also depending on the station density. But you can see to some degree, the space-time delta V over V takes advantage of both the spatial and temporal resolutions. Now I'll move on to the real data application. We will look at the groundwater in Greater Los Angeles and try to see what new insights this seismic approach can bring. So to begin with, I'll introduce very briefly the hydrogeology in Greater Los Angeles. So this area comprises a number of groundwater basins. Primarily is this Santa Ana Basin, LA Central Basin, and San Gabriel Basin. So most of these basins are bordered by mountains and faults. They are also partly partitioned by municipal borders. It's worth mentioning that each basin is managed by an individual water district. So the groundwater in this region exhibits strong seasonal fluctuations due to the Mediterranean weather in California. So in winters, there are sometimes a few storms. So the groundwater aquifers are recharged by the precipitation. In dry summers, the groundwater will decline strongly due to well pumping for water supply. Another big significant feature in this region is that the two major reservoirs or groundwater basins is partitioned by this, say, white dashed line. So on this side is confined zone. It's characterized as a confined zone, meaning that there are extensive clay layers separating all the aquifer layers. So the clay layers are highly compressible, right? So this confined zone is the spongy part. In comparison, this part is characterized as an unconfined, meaning that there are not so much clay. It's basically aquifers with sands and gravels with very low compressibility. So this unconfined zone, they deform very little, corresponding to the seasonal fluctuations. With that, we can look at temporal changes of delta V over V. So this is my study area, the Greater Los Angeles, with a very dense seismic network operated by USGS and partly by Caltech. So if I use all the seismic broadband seismic stations, I could calculate the temporal changes in delta V over V. Shown here is the temporal changes from 2000 to 2020. You may notice the vertical axis is flipped negative upwards. This is for a more intuitive comparison with groundwater. So now upwards means more groundwater. The gray line shows the long-term change of delta V over V. As a comparison, I also plot the annual precipitation on the bottom. So you can see over the past decades, the groundwater in Greater Los Angeles generally are declining, right, shown by the gray line. This was due to the long-term dearth of precipitation in California or in Los Angeles in particular. But this decreasing trend was also interrupted very briefly by several increasing episodes. If we compare that increasing episodes to the precipitation, you can see they correspond to years with maybe a few storms, winter storms in Los Angeles. Superimposed on the long-term change are also the seasonal variabilities. Those are due to the annual or seasonal hydrologic cycles. Simply to simplify the problem, in winter it's mostly increasing due to rainfall or precipitation. In summer, it's mostly declining due to the heavy well. This plot, this time series is an average over the entire study area, right? With delta V over V, we also have very good spatial resolution. So now I'll move or say zoom in into a local scale comparison. So the blue line is delta V over V again, but this time it's only calculated within Santa Basin. And the yellow line is the hydraulic head measured by monitoring well in Santa Basin. So you could see over the past 2 decades, these two match very well with each other, both for the long-term trend and the short-term variations. This is very promising because it means that we could potentially use seismometers as alternatives to monitoring wells, which, if we could do that, we can avoid the high cost of, drilling and maintaining monitoring wells while increasing the spatial and temporal resolution for groundwater monitoring. So this is just one basin. As I said,
sorry, can you hear me? I apologize for interrupting.
Right.
If you could be kind enough to go back one slide. It's Alan Chatney with Explore. One question that arises here is, I noticed that, and maybe it's just a resolution of the graph, I noticed that the V over V appears to rise before the hydraulic head pressure or the hydraulic head rises. Is that expected that you would see that first? The change in velocity?
That's a very good observation. I won't say that's expected, but I do want to see, you can see the hydraulic head here is just seasonal measurement, right? I don't recall exactly because it's doesn't seem to be evenly sampled, but I would say maybe 3 or at most 4 sampling each year for this well. I think they do have monthly well data. I'll show that in the next figure, right? But because it's for delta V over V, I'll also talk about the time resolution later. But for delta V over V, it's continuous measurement, right? So basically, we have 1 measurement each day. But for groundwater monitoring well here, it's maybe if you have only 1 sampling once in 3 months, it's not so reasonable, I guess, to compare the phase here with this type of time resolution. Does that make sense to you? Okay. And here is just similar comparison, delta V over V with groundwater monitoring wells for 3 different basins. So this is Santa Ana Basin, as I showed previously. This is San Gabriel Basin, you could see, and this is LA Central Basin. So because these 3 different water districts, they have very different water management practices. So the long-term behavior of groundwater level is actually quite different. But you can see delta V over V is able to retrieve that for different basins. This shows the, say, ability of delta V over V to retrieve subwater shed scale groundwater behavior, which would be very useful in water management in practice. So what I've been showing so far are the temporal changes, right? We also want to see where and how this type of changes is occurring. That brings me to the imaging of delta V over V. So we divide our study area into 2 kilometer by 2 kilometer pixels and calculate the delta V over V at each pixel. Shown on this map is the amplitude of seasonal variations across the study area. So you can see the strongest or dominant seasonal variations in the reddish area is, say, concentrated in Santa Ana Basin. The boundaries seem to match well with the boundary of the basin. And also the strongest or dominant seasonal changes concentrate on the confined side of the basin, which I guess makes sense. But this is actually the first time people are able to image this type of delta V over V to this level. So we want to validate our imaging. To do that, we compare our delta V over V with deformation map inferred from INSAR. To be more precise, so this INSAR map is a measure of the semi-vertical displacement at surface, whereas our delta V over V is a measure of elastic moduli and bulk density at depth. Despite being different physical properties, you can see these 2 maps match pretty well with each other in general, both with the dominant changes on the confined side of Santa Ana Basin. The biggest difference between these 2 is perhaps this reddish portion in LA Central Basin appearing on INSAR but missing on delta V over V. So what's the reason for that? That brings me to one very unique ability of our seismic. That is, with different frequencies of seismic waves, we can really probe the subsurface at different depths because waves in different frequencies travel at different depths. So this map on the left-hand side is measured within one narrow frequency range, 0.2 to 0.8 hertz. If I use more, now from left to right are measured with decreasing frequencies corresponding to deeper and deeper depths. So you can see from shallower to deeper, the reddish portion seem to migrate southeastwards, meaning that the aquifer seasonal changes deepen southeastwards. But consistently across different depths, the seasonal changes all concentrate on the confined side. Now, if I display the INSAR map again, so we know the INSAR, the surface deformation, is basically a sum of the strain changes across the vertical volume. So if now I sum up the seismic velocity changes across different depths, they kind of began to ensemble what we see with INSAR at the surface. So this first serves as a validation of our seismic, a very new approach. Secondly, it means that compared to INSAR or basically geodetic study type of measurements at the surface, delta V over V or seismic could also help obtaining the depth information of the hydrologic behaviors. So these are basically the validations of our seismic measurements temporally and spatially. Before going on, I want to pause a little bit and see if there are any, say, quick questions that I could clarify. Okay, so then I'll move on to some case studies to see what we can do with this type of delta V over V measurements. So in this section, I'll talk about 3 case studies. One is the decadal or long-term net change. The second one is the human managed aquifer recharge. And third one would be the response to atmospheric river storms. Here is the image of the 20-year net change, 21-year net change from 2000 to 2020 in Greater Los Angeles. You can see the bluish color correspond to an cumulative increase of groundwater and red color to a cumulative decline. With this map, it suggests that in San Gabriel Valley and LA Central Basin, there are much less water now than, say, 21 years ago. But in Santa Ana Basin, the groundwater seemed to recover with a slight increase compared to the beginning of 2000s. This means that we observe opposite signs in these 2 adjacent basins. Why is that? When I first saw this type of image, I was very surprised because I'm a seismologist in training, right? So when I see this type of boundary on an image, typically I would say there must be a fault. But there is no fault here. It's basically just a county line, meaning that there is no natural barrier for groundwater flow. But because these 2 neighboring basins belong to different water districts, so they experienced very different water management practices. Over a long term, the groundwater change accumulation exhibits strong comparison between these 2 points. I'll show you a little bit more detail with this one particular year. So you see this top panel shows the precipitation from 2015 to 2023. And the lower 3 panels show the delta V over V in each of these 3 basins, Santa Ana, LA Central, and San Gabriel. One particular year that's interesting to me is here, or I could see one particular summer. So you could see in the summer of 2017, it was actually very dry. The winter of 2017, it was a very wet winter, but during the summer, there was basically no rain. Corresponding to this summer, in LA Central Basin, the water is declining. The San Gabriel Basin water is declining. That's what we could expect, right? Dry summer without rain. But in Santa Ana Basin, you do see the DV over V suggests a big increase of groundwater during this dry summer. So why is that? That's because Santa Ana Basin, or which is managed by the Orange County Water District, they have a lot of sustainable water management program, including several, say, water recycling program and a lot of, say, managed aquifer recharge. So during this epic wet winter in 2017, there were excess water from, say, Colorado River, from elsewhere in California. So Orange County purchased some excess of those water and tried to store those water in their basin so that they could use those type of water in later droughts. So among all the, say, managed aquifer recharge programs they have, some are this type of spreading surface ponds where they put water just above the very permeable, highly permeable basins, and that water sink and infiltrate and recharge the aquifers. And in Orange County, they also have those type of injection wells across the basin so that they could inject directly the water into deeper confined aquifer. So during this dry summer, say from April to December 2017, what we observe, the spatial distribution of this groundwater changes are shown here. So you could see in Santa Ana Basin, there are very strong increase of groundwater across the basin. As a comparison, this is the INSAR image of land deformation during the same period. They correspond very well to each other. Of course, with delta V over V, we do have the depth resolution, right? So this is a deeper depth, and you could see at deeper depths or the mostly confined aquifers, the biggest increase concentrate on the southeast side. And also this is a shallower depths, right? And so at shallower depths, you could see the groundwater increase is more spread out, right? Also, another interesting feature is that you can see at middle to deeper depths, the groundwater increase seems to concentrate in Santa Ana Basin, right? But at the very shallow depths, the groundwater seem to, extend to Los Angeles Basin, belonging to Los Angeles Water District or Water Replenishment Department. So I was told by people in that hydrogeologists in that region that actually, so Orange County, this water district, and Los Angeles Water District, they both run hydrologic simulations separately, right? The Orange County simulations, that model extends 3 miles across the borderline. And then the Los Angeles County, they also extend 3 miles across the county line to Orange County. But, for the area where these two models overlap, their results are very different, right? The Orange County says that their model suggests their water is flowing to Los Angeles County, but the Los Angeles Water District model is saying that, no, there's no water flowing to their county. So our seismic remote sensing can serve as an independent assessment. It's complementary to the hydrologic simulations they run. So coming back to the long-term image here, so I mentioned that we do have this very significant boundary between the two counties, the Orange County and Los Angeles County. There are also some other features that are interesting. For example, this blue area, this is the Los Angeles West Coast Basin. So this basin, you can see it's very close to the ocean, right? So to mitigate the seawater intrusion, the water district, they restrict pumping in this basin, and also they are injecting water to mitigate the seawater intrusion. So over the 21 years or the first 2 decades of 21st century, you do see increase of groundwater in this basin. And another small feature is this yellowish area in Santa Ana Basin. So it actually used to be a military site, meaning the groundwater were contaminated. So the Orange County Water District has been pumping water in this area on purpose so that the contaminated water don't, flow out, right? So with seismic, we do see the decrease of groundwater flow in this region. And also another minor feature is this is the Chino Basin. We also see small increase of groundwater as for some first to some decades. So this type of analysis shows that human activities can play a very significant role in shaping the shallow subsurface structures, compounding the effect of climate change. And this effect can now be verified and quantified with seismic analysis. And with this type of analysis, we also show that delta V over V can serve as a new way to access groundwater budget. Is independent from the hydrologic simulations based on wet data, precipitation, or stream flow measurement, and it's complementary to that type of data. Due to time limitation, I'll maybe be a little bit faster about the last case study. So this is basically the seismic hydrograph we had extended to more recent last year. And in comparison, the lower panel is showing a comparison. The pink line is the satellite gravimetry data, what they derived as the water equivalent thickness. So to be more precise, our seismic measures mostly the groundwater, and satellite gravimetry is a measure of everything that induce a mass change, including surface water and groundwater. But in general, they match very well with each other over the past 2 decades. On the top panel, I show the precipitation and the drought index again. So this drought index developed by US Drought Monitor is mostly based on surface water, meaning precipitation, stream flow, soil moisture, this type of surface water. And you can see by this definition, so during this very extreme drought during 2012 to 2016, almost 100% California was in severe drought by this type of definition. But with one epic wet year in 2017, you see it wiped away the severe drought from entire California, 0% left in severe drought. That happened again for the very recent drought. So during this extreme drought, you see almost 100% in severe drought in California, with one epic wet winter completely wiped away. This was just the surface water, right? You can see for groundwater, it's not the same, totally not the same. Groundwater just keeps declining and declining. It recovered a little bit during wet years, but never able to be back to pre-drought level. That means groundwater drought is delayed and much more difficult to recover than surface water drought. Considering that groundwater accounts for 40 to 60% of freshwater supply in California, we do need to take into consideration of groundwater components to have a better assessment of the total water deficit. It's similar in Texas. And also compared to GRACE, it's also vertically integrated measurements at the surface, right? But with seismic, we do have the vertical resolution, right? Now from top to bottom are measured with different frequencies corresponding to different depths. We call it vertical seismic hydrographs, or VSH, is to compare with our exploration seismologist colleagues. Exploration seismologists talking about VSP, vertical seismic profiles, all the time. Now we have vertical seismic hydrographs, VSH. It basically shows that there are a lot of wiggles. Don't be overwhelmed by those. But if you look at the accumulated changes, you can see at deeper depths, the accumulated groundwater depletion is obvious, much more severe than at shallower depths. Also, I want to show a zoom in here. This is for the last water year, October 2012 to, I think, almost October 2023. But what you see is this is the beginning of the 2023 winter storms. And corresponding to a series of winter storms, you see the corresponding groundwater increases extend to very deep depths. In comparison, we also have this Hurricane Hillary in August, which is a very brief, very intense, but single event in dry summer. So corresponding to this very quick event, the groundwater increase only extend to very shallow depths. The water just flow to the rivers in the Pacific, not much really reached the deep aquifers. So it's very difficult for the deep aquifers to be recharged. With that, we could also try to answer in a relative sense how much water was obtained by Los Angeles due to this 2023 storm series. And so the vertical axis is the depth from shallower to deeper. The horizontal axis is what we define as recovery ratio, meaning the recovered amount in 2023 normalized by the total loss since 2006. So you can see at shallow depths, the water content seems to fully recover, almost fully recover 90%. But at deeper depths, say below 50-meter depths, only about 20 to 25% loss during the past decades were recovered. This means that a single epic year of storm is certainly not enough to restore the groundwater depletion accumulated over the past decades. It takes many more wet years for the deep aquifer to fully recover. We also, very recently, we also defined a groundwater drop index based on this seismic analysis, which could be helpful for assessing the total water deficit for practical applications. With that, I want to summarize what I showed is that we studied the spatial temporal changes of delta VORV in Greater Los Angeles, actually from 2000 to 2023. The seismic measurements are verified by hydraulic tests, the time series verified by hydraulic test and GRACE, and the spatial imaging verified by INSAR. So compared to vertically integrated measurements, seismic can further characterize the aquifer behaviors at different depths. So it could provide information of, how deep we want to drill the wells, or say how connected the different layers are. So I also showed some case studies in Los Angeles using, say, the long-term 2 decades net change to access the managed aquifer recharge, and also the response of, say, groundwater aquifer to droughts and storms. It shows that delta VORV can serve as a new type of observation to promote data-informed water management. As I talked about, introduced at the very beginning, it's a very cost-effective, non-invasive approach. It's independent from hydraulic data and modeling. With its high spatial and temporal resolution, it can be helpful to fill data gaps to help calibrate monitoring wells and so on. I also want to mention that in California, in 2014, they passed this historic legislation called Sustainable Groundwater Management Act, or SGMA. Next year in Texas, we had similar legislation swift. With this type of legislation, they highlight the importance of statewide analysis of water resources, and the seismic approach can contribute to water solution. Looking forward, so I hope with the case studies today, I have convinced you that delta VORV can be a very promising 4D geodata set. It's non-invasive, cost-effective, suitable for long-term monitoring of groundwater. But I also want to say, as a measure of elastic properties, actually, delta V over V can be applied to study various of subsurface processes, including subsurface water. Some I mentioned also, hydrology in permafrost or different type of settings. Another direction that would be very where seismic would be very useful is about geoenergy. So we are applying this approach to geothermal production. I'll show you a very brief example. Could be applied to unconventional oil and gas operations, can be applied to carbon capture and storage. I just want to emphasize again, with this type of cold air wave interferometry, we do have very high sensitivity to discern the small changes due to, say, CO2 sequestration. And also, it can also be, I didn't have time to go into details, but I'd love to talk more about it offline. Can be also applied to study landslides, volcanic unrest, and earthquake causes. So I just want to show you briefly a example about geothermal. This is the geysers in Northern California, which by some definition is the world's largest geothermal field. And we do have a very dense seismic network in this region. And also I want to note that most of these stations are geophones, right? They are not broadband stations. And with this dense seismic network, let's say first, typically for geothermal fields, people are looking at induced seismicity, right? So the green line is the seismicity rate, and the blue circles is the injection rate. So it's observed at a lot of geothermal sites that the induced seismicity is kind of proportional to the injection rate. Now in the lower panel, I'm showing you the net volume change. So it's derived by production minus injection. So the yellow line, because it's production minus injection, is a little bit different than the blue line, which is injection. And now the orange line here is our delta V over V. So before 2012, it was a bit messy or noisy because there were not the dense seismic array. The seismic array only started in 2012. But after that, it's much better. So you can see the orange line, it matches very well with the net volume change, meaning that delta V over V is really capturing the changes, spatial temporal changes in pressure. It's pretty different than what we say infer from induced seismicity, because seismicity is rock failure or rock damages, right? But velocity change is a different property. It's mostly capturing the pressure front propagation. That would be also helpful as a complementary observation to understanding the, spatial temporal pressure propagation in geothermal site. And I also want to note, so you see after around 2019, there was this strong depletion, seemed to be strong depletion of volume or pressure. So we also managed to image this net pressure depletion. This is from shallower to deeper. You can see with delta V over V, we observe pressure depletion at shallow depths across the geothermal site, the geysers. But at deeper depths, it seems the pressure depletion is mostly concentrated on the northern side. Also, I want to notice that for this geothermal site, most of the average depth of injection wells is about 2.5 kilometers. The deepest could be as deep as 4 kilometer depths, meaning that this delta V over V is not only to be applied for very shallow groundwater aquifers, it can also be applied for deeper processes. With that, I'm just gonna, just to say there are all this seismometer, existing seismometers worldwide that we can use for large-scale analysis. If we're interested, because now we're with Justine and TCCS, we're hoping to apply this approach to Texas. For local scale analysis, we can also use portable seismic sensors or geophones. They're pretty affordable and can be used to study regions where there is more hydrologically interesting, but not so many earthquakes. Also, we're now trying to push forward the use of optic fiber sensing, which can also serve as a type of seismic instrument to do similar analysis on data field. With that, just briefly mention, we've been trying to push forward this technique regarding different aspects. The codes are available on my GitHub, and of course, I'd be happy to talk more details offline. And also, we want to just to say none of these approaches is perfect, right? The idea would be really to assimilate different types of observation to obtain a comprehensive understanding about subsurface processes. With that, I just want to say the case studies in Los Angeles are just a beginning point, right? We can now, using this profound 4D data set to study various of subsurface.
Hey, thank you, Shujuan. Well, I know that we're running a bit long on time, so I respect if folks have places they need to be, but I think hopefully Shujuan would be willing to stick around for a few minutes for some Q&A. Let's see here. Did anybody in the audience today have in person have a question while I read this comment we got offline? Yes.
Thank you very much. Really fascinating. I work in CCS, and so I'm interested, and that you mentioned that it could be used. And at the very end, you answered one of my questions is how deep can you go? Because 700 meters, you're not even to the zone where CCS occurs. You have to go deeper than that, but you said you could do it deeper in that geothermal field. My question is, how applicable is this in seismically quiescent areas? The Gulf of Mexico basin has next to no natural seismicity. There's a little bit on the edge in the Eagle Ford trend, but CCS is probably going to occur even further away from that. So how applicable would this be?
That's
where there's no seismic activity?
Right. So actually, ideally, we would hope to, find a region that's seismically quiet, because typically we need to remove the earthquake signals. Those are not the signals we want. What we want are ideally, evenly distributed random seismic noise. For regions, near the coast, the strong ocean waves would be very helpful. Very rural areas, say Tibetan Plateau, there are people trying to do the ambient noise tomography of the very deep depressed in the mental transition, that type of approaches in very rural areas.
Thank you.
I'd like to try to alternate back and forth with lots of people online, so I'll do this one really quick online. Spatial resolution and sensitivity to delta V over V should depend on distribution of sensors as well as frequency. The test of the impact of sensor distribution on resolution for classic tomography is the checkerboard test. Could you do something like this using the sensitivity kernels to quantify ideal spatial resolution across your study area?
Right. So probably I'll just briefly mention. So in Los Angeles area, the average spacing of the stations are, say, from 15 kilometers to 50 kilometers away. We use that type of station spacing, and we get a resolution of 2 kilometers by 2 kilometers. If we have much denser array, of course, we get much better spatial resolution. And to the question how to quantify the spatial resolution, actually, we just had this paper published last year using Voronoi tessellation combined by multi-resolution checkerboard test, which will give a straightforward type of quantification of the spatial resolution. Because in most cases, the station coverage is not evenly distributed. There are very, say, some areas with denser stations, some areas are not so dense. So to deal with this type of scenario, we use this Voronoi tessellation to do adaptive grade meshing, right? It's adaptive to the station density. With that, we could optimize the station density and also quantify or quantitatively assess the spatial resolution.
Just a very quick question, a very nice talk. So can you transform the delta V over V to the exact amount of water?
That's a great question. So there are ways to do that. So what we did so far is to do using a Wendy simplifies poroelastic modeling, taking into account the coupling between the deformation and diffusion. And for the deeper part, it matches very well with the observed velocity changes. For the shallow part, because especially for unconfined zone or above the water table, the Vedas zone is more complicated. Saturation changes, changes in soil moisture and things. It's a lot more to model. So our approach now is to use some well data or water storage change data to calibrate our observation to establish an empirical relationship between water storage and delta V over V. We are trying to do this with the data in Orange County. They agreed to share the storage data with us because they are managed aquifer recharge, so they know very well how much water they injected into the well. So that could help.
Thank you.
Shujuan, I have a question for you.
Sorry.
I have a question, if I may.
Introduce yourself.
This is Mehdi. I'm a geophysicist, and I'm very interested in the methods you are using, CODA wave interferometry.
Right.
And my question is that, my understanding is that what you recorded as CODA, these are like S waves, right? And the S waves are insensitive to the water content. So what you are measuring and what you see is not the water content in the aquifers. You are measuring something that I believe has a good correlation with the water content. And
the control box is the only one for the front sprinkler.
And I think what you are measuring is not the water content of the aquifers. You are measuring the compaction, the level of compaction, because the S waves are insensitive to the fluid content, right?
So to clarify, first, CODA waves is a combination of scattered surface wave and scattered body waves, meaning that it's a combination of S wave mode and P wave mode. So it's I can go into more details, but as the lapse time increases, there are mode conversion, right? So the partition of S wave or the ratio of S wave is changing along the CODA wave. But that's just to say it's a combination of both S and P. Also to your question, whether it's compaction or pore pressure, it's mostly pore pressure changes, okay? Because for, say for Central Valley, the compaction or say the permanent loss of pore space or collapse of the media is much bigger problem. For Los Angeles, especially Santa Ana Basin, they have been managing it very nicely. So you can imagine if there is a permanent loss of pore space. If that happens, when the groundwater level go back, our seismic velocity won't go back like to the pre-collapse level. That means over the past 2 decades, if there are say compaction, we would observe an offside between delta V over V and the groundwater level. But that's not the case in Santa Ana Basin. You can see. If you see this, we don't see a long-term offset between the two types of observation, which means that at least in Santa Ana Basin, the compaction is not a big problem. I also checked with the Orange County Water Districts. They agree. They say they've been monitoring their storage changes, water levels very closely. They manage it in a way that they never over pump it. It never exceeds the historic low. So they don't think there exists, say obvious or significant compaction in this region.
But my question, I ask it in another way. So, how much of your waves, your CODA waves, are P, and how much of it is S?
That's a good
And
question. Yes, so I can't say for this one because, as I said, as the lapse time changes, there are S wave basically there are body waves converted to surface waves and surface wave converted to body waves. So what I'm using right now is mostly scattered surface waves, but we are trying to develop a better model describing this one, a better model describing the coupling between scattered body waves and scattered surface waves. That way we can get a better quantification of the partition between S wave mode and P wave mode.
So we are well over 10 after. So thank you everybody for coming. I think we can call it there. There's lots of interest in this work, of course, and with all, I would welcome people to try to connect with Shujuan directly to kind of talk further offline. I thought this was a fascinating talk, and I personally am interested to see where we might take this in Texas. So thank you again, Shujuan. Thank you everyone for coming, and we'll see you next week for our next seminars.